Section 8.3, Systems of Linear Equations, Determinants. This is another way to solve a system of equations, and it has 4 objectives that we're going to cover. The first is to evaluate, so find a number for, 2 by 2 determinants, and then to use Cramer's rule to solve a system of 2 equations containing 2 variables. Then the third thing is to expand our determinant knowledge and evaluate 3 by 3 determinants. And then use Cramer's rule to solve a system of 3 equations containing 3 variables. And if you end up taking linear algebra, you'll learn a lot more about the properties of determinants, so we don't really need to worry about them too hard at this point. So the first objective is to evaluate 2 by 2 determinants. And it's just a formula that says if I have 4 numbers arranged in 2 rows with 2 columns, and I label them A, B, C, D as shown, then if I do A times D and subtract B times C, that number is called the determinant. So it's just a formula that says for this first example, we do 8 times 2 minus 4 times negative 3. So we'll have 16 plus 12, or 28. Then the second example will have negative 4 times 3 minus negative 5 times 2. So you just have to be careful with negative signs. Negative 12 plus 10, so negative 2. So it's just a number associated with that set of 4 numbers that's arranged in 2 rows and 2 columns. So we're going to use that to solve a system of equations using Cramer's rule. And I'm going to call it a 2 by 2 system because you'll hear that a lot. 2 variables and 2 equations. So the way Cramer's rule works is if you're thinking of the numbers in the determinant as the A, B, C, and D, and then the constants, the S and the T, are over here. If you replace the X column, the first column, with the constants column, so if this column replaces the first column, and you find that determinant, and then you divide by the determinant of the original coefficients, you'll get a value for X. And then if you take this ST constants and you replace the coefficients on the Y's with those 2 numbers and do that determinant divided by the same original determinant, you'll get the value for Y. Of course, that's only going to work if the determinant AD minus BC is not 0, because we can't divide by 0. So Cramer's rule doesn't always work, but we'll talk a little bit about that at the end. So there's some helpful notation just to make it shorter to write these determinants. And if you replace the X coefficients with the constants, that one's called D sub X. And if you replace the Y coefficients with the constants, that one's called D sub Y. So then we can say the X value is going to be D sub X divided by D, and the Y is going to be D sub Y divided by D. So let's do the first one here, and then we'll do a couple more in class. If I want to find the value for X, I take the 13 and the 12 and make them the first column of the determinant. Then the coefficients of the Y are negative 1, 3. So that's my numerator determinant. Then in the denominator, I'm going to have 5, negative 1, 2, 3. So it's good if you keep track of what the denominator is because you need it again to figure out the Y. So in the numerator, I'm going to have 13 times 3 minus 12 times negative 1. And in the denominator, 5 times 3 minus 2 times negative 1. So I'm going to have 39 plus 12 over 15 plus 2. So I'm going to have 51 over 17, which is 3. And then y is going to be, keep the x coefficients, but now replace the y coefficients with the constants, the 13 and the 12. And now because we saved out that bottom determinant's value so we could see it, we can just use it again and we don't have to figure it out again. So my numerator is going to be 5 times 12 minus 2 times 13 over 17. So that's going to be 60 minus 26 over 17. So 34 over 17, or 2. And make sure you still remember to write your answer as an ordered pair. Okay, we'll do the other two examples in class. Then the 3 by 3 determinant, evaluating it takes a little bit more work. It's not quite as simple. So we're going to evaluate a 3 by 3 determinant. But somebody has already worked out a way to kind of leverage or recycle our knowledge of how to do the 2 by 2 determinants. And it's called expanding the determinant. You can expand a determinant along any row or column. And the 2 by 2 determinants that you get along the way are called minors of the 3 by 3 determinant. So it's easiest if we just do one, so you see how it works. So this determinant that we have, it says find the minor 1, 2. So if we look back up here, it says 1, 2 means block out row 1 and column 2 and write the 2 by 2 determinant that remains. So that's the minor 1, 2, and then that's a number. 1 times negative 2 minus 1 times 5, so that's going to be negative 7. And then M23, I cross out row 2 and column 3 and write what's left, the 2 by 2 determinant 3, 4, 1, 2, which is the number 3 times 2 minus 1 times 4, or 2. So that's a value that's called the minor. Then some of the minors get added and some get subtracted. And it depends on whether the row plus the column number is odd or even. So there's another number called the cofactor, which is the minor with its associated sign, whether that's positive or negative. So A12 is the minor 1, 2 times negative 1 to the 1 plus 2. So negative 1 to the 3 is negative 1. And then I got negative 7 for my minor. So the cofactor is positive 7. Then for the cofactor 2, 3, I'll have negative 1 to the 2 plus 3 times the minor 2, 3. So that's going to be negative 1 to the 5, which is negative 1, times the 2. So the cofactor 2, 3 is negative 2. So to actually do this, I'm going to suggest that you think about it first and say, well, I see a row or a column that has a 0 in it. So it's always easier if you expand along a row or column with a 0, because then you end up with a 0 multiplying. So I'm going to expand along this row. So my result is going to be, I take the 1, that's the first number in that row, and then I'm going to find the cofactor 1, 1, and then I'm going to have plus 4 times the cofactor 1, 2, plus 0 times, we don't really care what, because it's going to be 0. So we're going to get 1 times what's left after I wipe out 1, 1, plus 4 times what's left after I wipe out 1, 2. So that's 3, 4, 8, 1, and then 0. And then the sign for 1, 1 is going to be positive, but for 1, 2, it needs to be negative. So we're going to get negative 9 times 1 minus negative 3 times 4 minus 4 times 3 times 1 minus 8 times 4. So that's going to be negative 9 plus 12 minus 4 times 3 minus 32. So I'm going to have 3 minus 4 times negative 29. So it's going to be 3 plus 116, so 119 is the value of that 3 by 3 determinant. Then we'll do another one in class together because it takes a while to get the rhythm of this. So then we can use Kramer's rule again in the same way as before, where we replace the column that corresponds to the letter we're solving for with the column of the constants, and then keep the rest of the numbers. Then to solve for y, you take the constants and put them in the y column of the determinant. To solve for z, you put them in the z column. And look at all the different patterns that you can see of what gets left and what gets replaced. So Kramer's rule will break down if the determinant of the denominator is 0, but we can tell whether the system can't be solved because it's inconsistent, so there's no solution at all, or whether the system is consistent and the equations are dependent. So suppose you get 0 for that determinant. If at least one of dx, dy, dz is not 0, so you get a number for one of those, then the system is inconsistent and there's no solution. But if you get zeros for all of dx, dy, and dz, then the system is inconsistent and the equations are dependent. So you need to use some other technique to figure out how to solve the system. So we'll do an example in class with the full-on Kramer's rule for the 3 by 3 system. And that's all for this movie.